Our first speakers this morning are Bryan Dickman from Valytic Consulting and Joe Convey from Acuerdo. They're both independent consultants and CEO. Bryan has over 22 years of leading engineering teams and engineering communities in the field of design verification for ARM processors, and is a previous speaker here when he was at ARM. In recent years, Bryan's more focused on leading the effort to exploit engineering's vast data resources to drive insights and improvements to critical workflows, currently working as an independent consultant and founder of Valytic Consulting. Joe is 14 plus years in semiconductor EDA, has a close relationship with engineering management to understand their needs and provide best-in-class engineering platform. Promoted commercial awareness and engineering teams show the value of partnership with EDA vendors as a methodology to get optimized results from their tools and services. In-depth experience negotiation with major EDA vendors to ensure delivery of a resilient platform with acceptable commercial needs. I hand over to Bryan.
Thanks, Mike. Very nice to be here again and see everybody face to face after a few years. So Joe and I are going to talk today about bugs. We know that there's a lot of really interesting talks here today about verification challenges, technologies, and all the exciting things that are going on in the verification industry. But we want to kind of bring it back up a level and talk about bugs initially. So Joe and I have spent the last 3 years talking about bugs to a lot of people in the industry and trying to get people to think about the importance of bugs. And we characterize it as a resource-limited quest. If you think what a quest is, it's a long and difficult search. And that search, as we know, involves cost, resources, intellect, methodology, tooling. We all know here well and good how difficult verification is. And we also know that you can't actually find all the bugs. It's a somewhat non-tractable problem. So it is that question that is constrained, I think, by all these constraints. I think our talk today is going to hopefully give you some food for thought. So we're not here to give you a long technical pitch on some new technology. We just want people to think about things back from the aspect of both. At the end of the day, that's what we all care about, isn't it? Delivering designs that work. So who are we? So thanks for the introduction, Mike. One of the things that I've been thinking about over the last probably decade really is how much verification engineers are also data analysts. We deal with a ton of data, don't we? But I don't think we necessarily always know how to exploit that data. We have massive amounts of valuable data from verification work, verification activity, but do we really understand how to use that data and what can we learn from it? So that's kind of what we've been thinking about when we've been talking to our clients, is how do you exploit the data, how do you get the value out of the data, and how do you use that to improve what you're doing. At the end of the day, it's all about the ROI of the product that you're delivering and doing that efficiently and effectively. So we all love our jobs, don't we? Everybody go, hell yeah. But seriously, there's a lot of really cool and interesting and absorbing technology that we all learn about through perspective. Why it is a cool and interesting career path. Not necessarily something that has been particularly well taught through universities maybe, but as people come into the industry and they build careers in verification, you get to realise how deep the topic is. And we all get to use a lot of really cool EDA technology that has evolved over the years. And I've witnessed the evolution of a lot of that technology, from 25 years ago, really. And it's still evolving today because the problem's getting bigger. We know that the chips are getting bigger. The problems don't get any easier. In fact, probably what's happening is actually verification technology has done a really good job of just about keeping up with the complexity growth over the last 10, 15 years. So However, at the end of the day, it's a game of bugs, and we articulate it as a game of two halves in terms of bugs. So don't lose problem with the fact that you need to be able to find all the bugs and the effort involved in actually finding those bugs. But also, we're trying to elevate people to think about, well, how do I actually avoid bugs? So given that I know I cannot find all the bugs, what can I do to also avoid putting bugs in there in the first place? And I think that's important to keep those two things in mind when thinking about bugs. So one of the things that we've talked about is we articulate the problem as a set of dilemmas. Actually, Joe and I have written quite a few articles and white papers around some of those topics. If you want to explore it further, you can look at that. Everybody, I think, in this room is going to recognise these dilemmas. And the number one dilemma, I think, for everybody is completeness. How can you be complete with verification? You can't. And it's in all dimensions, actually. So you think about, well, can I be complete with coverage? Can I be complete with formal verification? Okay, formal sounds good because it has some concept of exhaustive enough, but actually, have I got a full set of properties to describe my behaviour? Probably not. Is my test plan complete? Have I run enough constrained random cycles? Have I run enough real-world system payloads on my design? So the whole bunch of different things that make you realise that you cannot be complete in everything you do. As verification engineers and design engineers, we're constantly using our engineering judgment and our experience to take a read on where we are at any particular time. And that's all driven, of course, by complexity. We've already mentioned complexity growth, and this is seemingly an exponential curve at the moment. We're talking about $1 billion ASIC, getting ASICs. I probably are $1 billion actually, and that's always the challenge, isn't it? Keeping up with that complexity and how to deal with it. But is that complexity always necessary? Can you understand the complexity? And if you can measure it and understand it somehow, can you reason about complexity, make decisions about, can I actually simplify this, reduce complexity, reduce the risk? It's all reducing risk from verification. We're all familiar with constrained random, and that constrained random workflow's been around probably 25 years, I would say, since it first saw that coming in. And it's mainstream verification these days, isn't it? But my word, you can consume a lot of resources with a constrained random approach, and actually it doesn't always find all the bugs. It doesn't necessarily go into all of the deep dark corners. So it's constrained random on its own, doesn't find everything. So that's a dilemma. Resources are clearly a dilemma. We've got limited resources. You've got to work within your resource constraints and your costs. And if you go over that, then you're really looking at eating into the ROI of the product that you're delivering, aren't you? So you've got to think about resource costs as well. And then at the end of the day, you've got to deliver something. So how do you make that judgment call about what's good enough? Have I done enough? Will it work? Does it meet the requirements? So just thinking about some of those challenging dilemmas that we're all dealing with. Also thinking about, well, where do bugs come from? So I think this is a useful thought exercise to think about, okay, I've got all these bugs, but if I actually really look into it, where are those bugs really coming from? What are the root causes of those bugs? What are the common ways that they get introduced into designs? But also, what can verification engineers and design engineers together, what can they do to try and minimise the amount of those bugs that go into these designs and really avoid bugs, actually? So I've used this from Harry Foster. I know Harry's talking later this afternoon, and this was his 2020 verification study. So there's some really good data from Harry. I don't know if he's doing an update for this year or next year, but
He does it every 2 years.
I mean, it's normally every 2 years, yeah. I don't think that's what he's talking about today, though, is it? No. So I pulled out a couple of Harry slides because I think they just illustrate really well some of the analysis around things like root causes. This suggests that most of the root causes are down to design errors, but there's also a significant proportion of down to spec errors. Spec errors, spec interpretation errors. we're all familiar with the spec creep, spec change issue. So those are some of the root causes. The other thing that we're trying to get people to think about is actually the scope of what we mean by a bug. And traditionally, historically, we always think about functional bugs. But actually, there's a lot more to that. And there's a lot of things that are going on these days, that like power and security, functional safety, and there can be bugs in those areas as well. And there's value, I think, in treating everything with a bug approach. So in terms of how you analyse things, whether you root cause it, you look at the analytics, you look at the data. It's important just to characterise all of these things as bugs. They are all subsets of bugs. And I was going to go into a couple of quick examples. So power bugs, for example. So again, there's another chart on power showing how much power architecture is becoming dominant in modern basic designs. But those are really important areas where bugs can be found. They're found through different ways. You find them with power analysis type techniques. They may not appear to be necessarily functional bugs, but if you don't meet the power target, it's a bug. You're going to go fix the RTO. Security bugs, different kind of breed of bug altogether, actually. And again, very much emerging as a real problem in recent years. Many of you are familiar with the old Spectrum meltdown bug a few years ago, and there's a lot of stuff out there about that. Those are real challenging problems, and again, your design may appear to work completely functionally okay, but if you've got some vulnerability in there, some weird sequence, convoluted sequence that is known about, then it will be expensive, and you'll have a security creep. So again, think about those things as bugs. And then hopefully everybody gets my joke, the automotive bug here. So functional safety again, different techniques to find problems in designs and the consequences of these things are slightly different. It affects what ASIL level you might achieve, for example, but a bug in a complex safety mechanism is still a bug at the end of the day. So quickly, just thinking about, or how do we find bugs? This is something that we talk to people a lot about, is thinking about capturing the data around how you found the bug. And if you do this, what it helps you do is reason about the effectiveness of different methodologies. So you might go, well, okay, well, I found quite a lot of bugs with simulation, but I don't think I'm really finding enough with formal. So maybe I need to invest more in formal. Or how come I found so many bugs by just eyeballing and reviewing, for example? So something. Yes, it was, wasn't it? I didn't do that deliberately, either. So more stuff comparing. I'm moving on quickly now. Again, you can look at Harry's survey. He's got some interesting data on root causes. And then my final slide before I hand over to Joe here. Just thinking about root causes. I'm a big believer in making marginal gains, marginal improvements. And if you do this root cause analysis, you can use each of those little inputs to make a small incremental improvement. And they all add up over time. So you make 100 of these small incremental improvements, then you can see a big effect. But one thing that we say to people is, please think about both aspects of this. So from the design point of view, why was the bug there? What caused that bug to be in the design in the first place? Think about that and what can you do to improve that? And then, why did I miss the bug first time around? So, what's wrong with my verification environment? But could I find that bug earlier and more cheaply? So if you found it quite late on, for example, in emulation or worse still in prototype silicon, go back and look at your unit verification environment. Maybe not. Could I have done that? Could I have done that soon? I'm going to hand over to Joe. Joe's going to talk about something else that we've been working on, which is the cost of bugs. Very good. Thank you, Bryan. Give you a clicker. Yep.
Good to meet you all, everyone, and this is my first time here at the event, so the first, and slightly weird talking to an audience from venues like this. So, as Bryan said, I'm going to talk about cost of bugs. I'll move on to that. Bryan talked about verification is a very complex and hard job. It's also a very expensive job. So one thing we've been doing is we're talking to the industry in our protocols, is trying to understand what that looks like and trying to give you some of those thoughts today as well. So it's an expensive process, and actually it comes in two flavors. You've got the cost of actually doing verification, and then the cost of not doing a good enough job. In other words, there are escapes, and not finding bugs is equally important. So we'd like to talk to you about that today. This won't be a surprise to most of you. Bryan and I are real fans of doing whiteboardy stuff. So let's just talk you around when bugs are found, which is a good place to start a conversation about what's happening. So, not surprisingly, you're looking at bug rate here and work rate. And a lot of the experience you'll have had, most of you, I think, is that a lot of the, as much as 90% we're postulating this, are found very early in the process. It's only when you get further down the process of finding bugs that the real effort comes in. So a great deal of effort goes into this latter period here when you're finding the more expensive to find bugs, very difficult to find, and quite often the ones with the biggest consequence if they escape. So it's very important when you're looking at this to understand when you're in that process or where you are in that process and be able to reason about where you are in that process. So an underlying theme in everything we're doing with our customers is understanding both analytics, and that includes work rate, but there's also another curve you could add on to this, which is the investment cost rate, which raises up as you go through that process. So that helps you reason about the workflow methodologies that you're currently using, the improvements you need to make in order to improve your chances of capturing those bugs at the end of the process. But it also forces you to think more carefully, or should make you think more carefully about how you track that information, what information you actually want to capture. So let's have a look at one of the major contributors to cost, and that's the, we call it the engineering platform. So again, this won't be a surprise to any of you, but there are some major elements of cost in this diagram here. The EDA tools, obviously, we're all familiar with the cost of those tools. As Bryan said earlier on, they're fundamental to actually making sure we can find these bugs. Certainly in my previous life, buying tools for ARM, we spent a great deal of money at that end of the process. But equally, there was a large investment, and you'll find this in your own companies, in the platform underneath it. So certainly on cloud, that's an interesting story to have a look at. But today, most of you, I would guess, are probably still using on-premise or colo type CPU. There'll also be investments in FPGA and emulation. So there's a lot going on in this area. And particularly thinking about cloud in the future, there are some changes happening at the orchestration level as well. There's some interesting companies out there looking at that with a view to trying to help larger companies with a big investment in on-prem to manage what you might call a hybrid cloud on-premise type combination. Now, the problem with that, obviously, is when bugs come out, and they do escape, as Bryan mentioned earlier, it's a completeness problem, a dilemma that you mentioned earlier on. Then there's a huge pressure. If you think of the balance between the cost of bugs here, a bug escapes, there's an immediate reaction from customer. Customer will probably oblige you to do a root cause analysis, quite a painful process. They'll expect to understand what you're going to do to actually rectify the situation so there isn't an escape next time round. And that usually translates into a rush around to do rework, and certainly people costs to do that, platform costs and tools. So there could be some big costs incurred there. And at the same time, there's a risk, another cost, which is reputationally, unless you can provide that customer with a good answer, then there's an impact potentially on revenue. So the sales and senior leadership of your organisations are going to have to front up to that customer and try and explain what happened. But there is a risk that the customer turns around and says, well, next time we're going to go somewhere else, or next time we're not pay you as much, etc. So trying to get that balance right between the investment you're making in the tools, people and platform and the impact it has on sales is a really tricky balance. And again, in order to understand that, you need good analytics to explain what's happening under the hood. Move on to the next slide. Right. So the next slide, of course, that picture we just showed is really a picture of constraint. Like I mentioned earlier on, one of the dilemmas is, nobody's going to spend infinite amounts of money on the platform. So here's the fake data that we put together to explain a typical sort of scenario with a number of projects running in any one company with a fixed capacity level there. And it shows a couple of things really. At one point you've got over provisioning because there's not a lot happening. Then you have a spike of activity with a capacity shortfall, and underutilization again. And eventually you get to the point where there could be a very significant project comes along where there just isn't enough resource. And if you don't plan for that, there's a mad scramble to try and get a new resource on board. And it could be FPGA, it could be CPU requirement, to do more simulation, etc. And somebody's got to persuade senior management to invest heavily to rectify that situation. That doesn't just happen like that. So it needs to be planned for, and it costs a great deal of money to rectify. So again, the drive there is going to be on more compute, potentially other alternatives, and that's where a lot of companies are now looking at cloud as an alternative. So I don't spend a lot of time on this because it's kind of, I think, something that a lot of you will be exploring. But there is a real opportunity here if you have a resource-constrained engineering platform to do things differently with cloud. And it's certainly something we're explaining and exploring with our customers. There are some great opportunities to run faster, run leaner, etc., as you can see on the left-hand side. From a smaller organizational point of view, it's a great opportunity to get off the ground and get a level playing field with bigger organizations as well, because you could go to an EDA vendor and get all-inclusive software as a service type deal, or emulation as a service, or FPGA as a service type deal, and compete with bigger companies who've got huge investments in on-premise already. So it's got a lot of opportunities there. However, it's not a no-cost option either. But it does have another advantage, which is you have one OpEx line with all your costs on there. So from a verification point of view, it offers up the possibility of being able to track your actual workload, but also to be able to track the costs per cycle of activity, etc. So to get a better idea of your verification effectiveness. So that's something that we're tracking quite closely, and we want to be able to talk about more in the future. The other thing we wanted to draw your attention to was, which scenario are you in today? So there's something to point out here. The cost of finding bugs is the investment we've just been talking about, and then the cost of not finding bugs, which is the extra rework, extra tooling, impact on customers, reputational damage, etc. Which scenario are you in? Are you in this scenario here where you're possibly not spending enough money and there's a dramatic effect in terms of those costs? Not a great position to be in, and nobody wants to admit being in that position. Or are you in cost scenario B, where you may be feeling, right, we've got it covered, but actually it's costing us too much money? And unless you've got really good analytics that explain to you where you are on that spectrum, you run the risk of falling somewhere in between, or in the worst case here. And it's very difficult to react quickly in that situation and rectify the situation. So it's all about data and trying to understand where you are. And also, we were talking about this last night, the circle of life, or maybe the wheel of misfortune, as Scott maybe remembered last night. And where are you on this? And we're trying to think of a process whereby you can go through, having got some really good verification progress metrics, so you understand where you are in terms of science, etc. What's the impact then on the platform? You should be able to make a direct linkage between those and reason about how much extra platform do we need, and then put that into a business planning activity with an event horizon which is sort of 24 to 36 months rather than just right here, right now, we're in the crisis. And then that allows you to manage engineering platform enhancements in the correct way. And of course, then you want to measure using shift left metrics that you're actually doing the right thing at the right time. I haven't much time left for this slide, but there is a process, and actually this is a quite useful scorecard for you. If you think about data-driven decision making, particularly around sign-off, the right sort of questions you need to ask yourselves as an engineering organisation to understand, get the insights that Bryan was talking about, and then develop the analytical views that would allow you to make good decisions. And that has an implication in terms of data input, the sort of boat tracking information you're capturing, and then the behaviours, the cultural change you might want to have to ensure that you have a really clean verification boat tracking environment. So at the end of it all, it's definitely a story about boats. I think with the number of graduates in the room, it's also about data. Big plea to all you guys and girls out there to really think about how to use data and make verification more data analytic orientated as we go on. So that is that, I believe. As Bryan said at the beginning, we have written a number of papers there, so please do have a look at those.
Thank you very much. Maybe you don't want me to come across, maybe stick in. So Bryan, just a quick question on your bugs. Usually your bug data is about how many found bugs. There's a field in your bug database where you track. Is that right?
Yeah, I think it's all about having the right schema for your bug tracking. So yeah, you really got to think about collecting that good quality data. And it's interesting because I know bug tracking, can be seen as a bit of an overhead, particularly slowing down the design process maybe. But the value of having that data, if you can do good analytics and you can ask good questions, get good insights from it, is the reason for doing it. And, you have to convince people sometimes what they're doing.
And just one concern ahead. So you maybe the verification activity you do first may score higher because it finds the bugs others would have found versioning numbers. Is there any other way to overcome that misleading data?
But yeah, I mean, you have to really get back into the data for sure. Yeah, if you're going to do, you did formal verification first and then do simulation, you're probably going to find most of the bugs before. So absolutely, you have to contextualize your data with that knowledge for sure.
Again, we're spot on time, so thank you very much.
Okay.
Thanks, Joe. Thanks, Bryan. And we'll find out our next week as well. Thank you.